Hey y'all, this is Mrs. Tran-Bloom speaking again for Chapter 6. So today we're going to start graphing some functions that has some interesting transformations, right? We did all the parent functions already up to this point. So today we're going to use key points to graph. That means we're not going to do it in stages. So if we were to do it in stages, I would need 3 different graphs for this. But because we're going to use key points, we are only going to need to graph it one time and only one time. Alright, so before I start, I normally do tell you a toddler's joke, right? But I always end up forgetting at the end. So I should make a point to tell you a toddler joke at the beginning. So today's joke is this. Why did the student get upset when his teacher called him average? So why did the student get upset when his teacher called him average? He was upset because it was a mean thing to say. And mean is spelled like this. Mean, okay? It was a mean thing to say because mean is another word for average. Ha 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 ha. Anywho, that is my toddler joke for today. And if you don't know me, I normally sort of, if I remember, tell you a 4-year-old joke, alright? So, example 1, use key point to graph. State the domain and range, determine the amplitude and period. Okay, so let's do that first. The amplitude and period. As we remember, let's put my average joke on the corner here. As we remember, this is the tangent function. And for the tangent function, there's no amplitude. So that's sort of like a trick question, right? Amplitude, there's none. So box that up. Because it says determine it, so we want to say, hey, if there's none, we're going to say none. Period, we are going to say for the tangent function, it's always pi divided by absolute value of b. And this is 2 times tangent of 1x, so your b is actually 1. Okay, so pi divided by 1 is just going to end up as a pi. So you have a period as a pi, so I'm going to go pi to the right. I want 2 full cycles all the time, so I'm going to go 2 pi, so that's 2 full cycles. So each cycle has 4 equal parts, so I'm just going to go in and put my tick marks in. So half of pi is pi over 2, half of pi over 2 is pi over 4. So each tick mark is worth a pi over 4. So 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4, 8 pi over 4 reduces down to 2 pi. We can also go left as well. Excuse me. So the first thing I'm going to do is I'm going to write the parent out. Even though I'm not graphing in stages, but I'm still going to find my points in stages. So the parent function is y equals tangent of x. So let's find 5 points. Okay, 5 inputs. 0, pi over 4, pi over 2, 3 pi over 4, and I want to end up at a pi, okay, because my period is a pi. Okay, so the parent function of tangent, y equals tangent of x, tangent of 0, if you guys remember, tangent here is 0, right? And if I were to label that dot as 1 comma 0, and because it's in a unit circle, it's y divided by x. So 0 divided by 1 is going to be at 0. Then tangent of pi over 4, it's always going to be 1. Tangent of pi over 2, here's the dot of pi over 2. This is labeled 0 comma 1. What happens when you take y and you divide it by x? I hope you're writing down undefined. And tangent of 3 pi over 4, this is going to be a negative 1. And back at tangent at pi, which is going to be 0. Okay, so this is all the inputs and outputs for the parent. You have a couple of transformations here, which we're going to talk about. We have the 2 in the front. Okay, so that's a vertical. This is your vertical stretch factor of 2. You have a minus 1 in the back, so this is going to be down by 1. Now a vertical stretch, just like the way it sounds, is going to be changing the y value. So my input and output, okay, So that's going to be a y change. And a down, it's also a y change. So it looks like there's nothing changing the x. So x is going to be staying the same. But I'm going to take my y value and I'm going to multiply it to a factor of 2. So 2y, and then moving it down by 1. So 2y minus 1. Because it looks like everything is affecting the y value. So this is sort of the new table or new formula that I'm going to use, right? So x, I'm going to put all the x values back, which is, as we said before, none of the transformation here is going to change my x values, my input. So I'm going to write it exactly the way it is, okay? But I am going to use my y value. So 0 times 2 is 0, minus 1 is now negative 1. 1 times 2 is 2, minus 1 is positive 1. Undefined times anything is undefined, okay? And subtract and add, it's still undefined, unless you move left and right. But because we didn't really change left and right, that's still going to be undefined. Negative 1 times 2 is negative 2, minus 1 is negative 3. 0 times 2 is 0, minus 1 is going to be negative 1. So these right here are the point I'm going to use to plot. And let's use, I'm going to use red for asymptote. The first asymptote is going to be at pi over 2. So here's my asymptote. Okay. And I'm going to plot this dot right here, 0, comma, so I already plot this one, check. 0, comma, negative 1, here's 0. Oh, I should make a positive 1 and negative 1, right? So positive 1, negative 1, negative 2, negative 3. Okay. So 0, negative 1, so it's right here. Pi over 4, positive 1. Pi over 2, asymptote, I already have that in. 3 pi over 4, 1 pi over 4, 2 pi over 4, 3 pi over 4. Looks like I need to go down to negative 3. And at pi, which is this one, looks like I'm going to negative 1. So check out the dots. Over here, I have a dot at negative 1 and then positive 1. Over here, I have a dot at negative 3 and negative 1. I'm sorry, negative 1 and positive 1. So the next pattern looks like I'm going to go to the next tick mark and go to positive 1. Then the next pattern over, I'm going to have it as another asymptote. Because it looks like there's an asymptote every fourth tick mark over. Then I'm just going to repeat the pattern. Since after the tick mark is going to be after the asymptote, I'm going to go right one tick mark, go down to negative 3. And then over, and then we're going to have a positive 1. I'm sorry, a negative 1. Okay. So if I were to connect the dots, remember this is not a straight line. It's sort of like this, right? It's hugging the asymptote. Over here, I can do the same. But because I only have 2 dots, I'm just going to do that. Over here, I'm just going to do this. So if I put these together, they'll make one nice curvature here. And if you really wanted to, we can make another tick mark over here, and then another tick mark. So this is a negative pi over 2, going above and beyond my 2 cycles here. Okay, and if I wanted to, I could make another cycle on this side, so it doesn't look so weird. And then make a dot at one tick mark to the left, which is a negative pi over 4, comma, negative 3. So we're going to connect that. You didn't have to do that extra step because technically I do, from here to here, I do have 2 full cycles. So we can stop right there. Alright, so the next piece it says, hey, state the domain and range. And you do have to understand how to write the exclusions, okay? So the domain is going to be easy. It's going to be all reals. So your domain, I'm sorry, not domain, the range. The domain, we're going to leave it blank. But the range, that's quite easy, all real numbers. Negative infinity to positive infinity. Okay. So what are we excluding for your domain? Looks like we're excluding negative pi over 2. And then a positive pi over 2. Then this is a pi over 2. This is 2 pi over 2. This is 3 pi over 2. So if I write a list, dot, 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 right? X not including. Negative pi over 2. The next one is positive pi over 2. So if this is positive pi over 2, this is 2 pi over 2, that's 3 pi over 2. Okay, dot, dot, dot. Would you agree? And from here to here, okay, what am I adding? So from pi over 2 to 3 pi over 2, what are we adding to get to this? I hope you are saying 2 pi over 2. And from here to here, I'm also adding 2 pi over 2. So if you're adding a constant unit every time and reduce that down to a pi, then that's what we're going to use. So domain is going to be all real numbers, not including, I'm going to start with the first positive value here, which is pi over 2, plus, I'm adding a pi every time, right? So from here to here, I add a pi. From here to here, I'm adding a pi. But I can't just say 3 little exclusions. I have to say for all of tangent graph. So pi k, I'm excluding it. Where k is any integer. Where k is any integer. Okay? So that's, and then box that up. Okay. Okay, so let's quickly test it out. So when k is 0, do I have an asymptote pi over 2? Check. When k is 1, 1 pi plus pi over 2. That's 3 pi over 2. Do I have 1 at 3 pi over 2? Check. 1 pi, when k is negative 1, it's 1 half pi over 2 is 1 half pi plus a negative pi. Am I going to end up with an asymptote at a negative pi over 2? And that is also true. So all of that matches with the asymptotes. Alright, and our next example is going to be graphing secant. Y equals negative 3 secant of pi divided by 2. So the first thing we are going to do is find the amplitude and period. Okay. I'm going to do this one in probably pen to separate, you know, my example A and example B. Amplitude. No, this one's not really working well. Oh, there it is. Okay, amplitude. Amplitude for secant, there is no such thing. Okay. Period is going to be the same as, because this is the reciprocal function of cosine, it's going to be the same. Oops. Period is going to be 2 pi divided by absolute value of b. Okay, that is supposed to be 2 pi. 2 pi. Your b, this is negative 3 times secant of pi over 2x. So this is your b right here, pi over 2. So 2 pi divided by pi over 2. And if I multiply by its reciprocal, which is really 2 over pi, and the pi's will cancel each other out. So 2 times 2, this is 4. So I have a period of 4. And don't be scared. You don't have to, the x-axis doesn't have to be in pi term all the time. You can just be 4. There's nothing wrong with 4. So 1 full period is 4. So that means 2 full periods is going to be 8. Okay? So each take mark is worth 4 intervals. I'm sorry, each period's worth 4 intervals. So each take mark is a unit, which is nice. Okay? Now let's make a table for your secant. Okay? So parent function is y equals secant of x. Secant is the reciprocal of cosine. So if you really wanted to, we can also do cosine. Okay? X and y. Here we go. Inputs. We're going to use 0, pi over 2, pi, 3 pi over 2, and 2 pi. These are my 5 inputs. We're going to find the 5 output for secant of x, the parent function. So at 0, okay, here's my dot at 0. When the input is 0, cosine of 0 is 1. 1 divided by 1 is still 1. So secant at 0 is still 1. This one right here. When x is pi over 2, cosine of pi over 2 is 0. 1 divided by 0, it's undefined. So therefore, secant of pi over 2 is undefined. When at pi, when x is pi, cosine of pi is negative 1. 1 divided by negative 1 is negative 1. So therefore, secant of pi is negative 1. 3 pi over 2, which is this dot. When x is 3 pi over 2, cosine of that is 0. 1 divided by 0 does not exist. Therefore, secant of 3 pi over 2 is undefined. 2 pi is back to this 0, so 2 pi is the same as 1. Okay? So those are the 5 inputs and output for the parent function, y equals secant of x. Now you have 3 transformations here, and I'm just going to list this from left to right. Okay, so this negative in the front, it's a reflection about x-axis. Okay, this 3 right here, that's very similar to the 2 above. Okay, it's a vertical stretch factor of, instead of a 2, it's now a vertical stretch factor of 3. And this right here, it's a horizontal change because if you look at this, it's multiplying to x. So I know it's horizontal. And this is a pi, which is really, a pi is about 3.14. So don't be scared of 3.14. And if you remember from our experiments before, that if you, with the horizontal, you kind of have to take its reciprocal. So when I take its reciprocal, it's 2 over 3.14, which is a value that's less than 1. So it's a horizontal compression factor of 2 over pi. So I'm going to leave 2 over pi as 2 over pi. Okay. So you can't really stretch if you're multiplying a number that's less than 1. So that's why this is a horizontal compression. So now I'm just going to use which one is changing the x and which one's changing the y. Okay. Horizontal compression, well, that's obviously going to change the x because it says horizontal. This one's a vertical, so we know that's changing the y. So this is a y change, this is an x change. This is a reflection about the x-axis. So if it used to be on the top, now it's on the bottom. So you know that it's going to flip over, the y value is changing. So when I make my table, here we go. I have one thing that's changing the x. I'm going to go 2 over pi times x. 2 things that are changing the y. So I'm going to multiply my y by a negative because the reflection right here. So negative, and then also not just negative, negative 3y. So that's what I'm going to do with my original inputs and outputs. I'm going to change it in this format. So 0 times 2 over pi is still a 0. 1 times negative 3 is now negative 3. Pi over 2 times 2 over pi, the 2 will cancel each other out, and the pi's will cancel each other out, and the 2 will cancel each other out, so that will give you 1. And undefined, it doesn't really matter. That's an asymptote. An asymptote, when you are going to stretch it or reflect it, it's still going to be an asymptote. So notice how now we got 0 and 1, and increment is by 1 unit. How about what happened when I take a pi and then multiply to 2 over pi? Okay, so pi times 2 over pi is simply 2 because the pi's will cancel. And negative 1 times negative 3 is going to be a positive 3. So check out the pattern on the x and the inputs. You got 0, 1, 2. So you know the increment. Okay, the increment on the x value is going to be by 1 unit. So I'm going to be safe to assume the next one is going to be 3. So, because I have 5 of those, right? 5, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Then I just need to write 5 over here. 0, 1, 2, 3, and okay. And then this is 4. So that's my 5th input. Okay. Even though it says number 4. I know it's kind of weird. Alright, so at 3 pi over 2 times 2 over pi, that's now 3. My output happens to be an asymptote, so over here is still going to be an asymptote. 2 pi times 2 over pi is going to give me 4. 1 times negative 3 is going to be a negative 3. Okay, so these are the values I'm going to use to graph out this particular graph of y equals negative 3 times secant of pi over 2x. Here we go. 0, negative 3, 1, 2, 3. Let's make those tick marks. Okay. 1, I'm going to make an asymptote. At 2, I'm going to go up 3. Make 3 tick marks. At 3, there's another asymptote. At 4, I'm going to go to negative 3. Okay. So it looks like the pattern is a dot down, an asymptote, a dot up, an asymptote, a dot down. It looks like I need an asymptote. And then now I need a dot up. Then I need a dot, an asymptote. Then I need a dot down, right? Okay, according to my little pattern. So, do you guys remember what a secant function is supposed to look like? A secant function Remember how you had those parabolas that's approaching the asymptotes on both sides? Right? Remember that? Because that's above, it's going to go up. This is below, it's going to go down. That's above, it's going to go up. This is below, it's going to go down on that side. I don't have another asymptote there, so I'm not going to approach that. And that's going to go down. And I want it 2 full cycles, so technically this is 1 cycle right here. 1 cycle includes 2 parabolas, okay? And if I put these together, that will make 1 full one, so technically I have 2 full periods. And that's how we graph our secant function with all of the transformations. Alright. Now we have one more on this page, which we're going to try to fit in here. And, oh, I'm sorry, I need to define the domain and range. Okay, so, excuse me, the domain, okay, let's talk about the exclusion. The first one I'm excluding is 1, and then 3, and then 5, and then 7. So let's list that out. I'm excluding, okay, dot, 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 1, and 3. I'm excluding all the asymptotes on my domain, and 5, and then 7. So there's so many different ways that you can do this. You can go 1 plus, looks like from here to here, I'm adding 2 units, right? And I'm adding 2 each and every time, so pretty much I can do 1 plus 2k, where k is any integer. Okay, so this is one option. You can also do, looks like I can even multiply, right? You can do 2 times k minus 1. How does that feel? Okay, one or the other. So how is that going to work? 1k is 0. 0 times 2 is 0. Minus 1. Would I have an asymptote at a minus 1? Which technically, let's see, is that true? I would have a dot right there, so over here is an asymptote. Would that be true? Yeah, I would, right? How about when k is 1? 1 times 2 is 2. 2 minus 1 is 1. I do have an asymptote 1. K is 2. 2 times 2 is 4. 4 minus 1 is 3. Yeah, that will work too. So your domain is, you can exclude. It's going to be all real numbers, excluding. You can write this multiple ways. 1 plus 2k or 2k minus 1. Look at that. How about we do 2k minus 1? Okay, where k is any integer. Alright, so there are so many different ways you can write the exclusions. In your range, let's talk about your range. It looks like from -1 and down, and +1 and up. I'm sorry, not 1, 3. -3 and down, and +3 and up. So we can write negative infinity to -3. Inclusive, my bad, inclusive at -3. Union that with 3 to positive infinity. So those are your domain, and that is your range. Okay. Okay, so we have, looks like we have 2 more here. So we're going to try to see if we can, no, let's not try to squeeze it in. It's already 23 minutes. And that is going to be the end of our today's notes. I'll see you guys next time.